This is lesson 5.4. In lesson 5.4, we're going to talk about the amount of solutions we have for our system of equations. So if we're looking at example 1, question A, we have two equations here. And in the past, we have solved by graphing. So if I place a point at 5 on my y-axis, I use my slope of -2/1. So I move down 2 and right 1, down 2 and right 1. Connect my line here. There we go. And then I do my second equation. I have a y-intercept of -1. And I have a slope of 4/1. So I'm going to go up 4, 1, 2, 3, 4, and over 1. 1, 2, 3, 4, and over 1. That third point just kind of helps me get my line a little straighter for me. There we go. And we notice right here, those two lines overlap. When they overlap in one spot, it means that we have one solution. And in this instance, that one solution is 1, 3. So when they overlap each other in one spot, we have one solution, and then you name it. Give it that point, that name. For example 2, we're going to graph. We have y-intercept of +1. We're going to go up 2 and right 1, up 2 and right 1. Just for reference also, since it's a positive slope, I can also go down 2 and left 1 because they're both a negative direction, and a negative divided by negative is a positive. In case you're ever in a situation where your graph doesn't have space to go one way or another, you can go either direction as long as you're doing either two positives if your slope is positive, two negatives. All right. And then for line number 2, I have a y-intercept of -5, and I have a slope of 2. So up 2 and over 1, up 2 and over 1, or down 2 and left 1. So what we're noticing here is that these two lines, it doesn't look like are crossing one another. So something that we'll notice is that when you have two lines that have the same slope, so notice here, slope of 2, if they have the same slope, we know that those two lines are parallel. And if the lines are parallel, that means they are never going to cross, which means we would call this no solution. So sometimes we're asked to solve these questions using things besides graphing. So if we were solving this one using substitution and elimination, just like we've done before, we would be able to solve for one variable, plug it in, and solve for the second variable. If we have a no solution, let's look at what it would be if we used substitution. So we're going to put that over here. So this is example 1, letter B. So for substitution, we're going to plug in, we have y equals 2x plus 1 and y equals 2x minus 5. So we know that y equals 2x minus 5. So we're going to plug that in right here. So I have 2x minus 5 equals everything else that was left, 2x plus 1. So when you go to solve this, right, we have to get our x's together and our whole number, our integers together. We're going to subtract 2x from both sides. When I do that, 2x minus 2x is 0. So I'll bring down my -5. 2x minus 2x is 0, so I'll bring down this +1. Does -5 equal +1? No, because it's not equal to one another. It's not a true statement. That's why I have that no solution. And then we recognize, oh yeah, they're parallel lines. Parallel lines will never cross one another, so there wouldn't be a solution, because the solution is where those two lines cross or touch one another. For example 2, it says, tell how many solutions the following system has. So we've got -2x plus y equals 3, -4x plus 2y equals 6. If I want to do elimination for this one, since it's in standard form, I'm going to go ahead and multiply this top equation here by -2 to get rid of these x's. So that gives me 4x minus 2y equals -6. And then we'll bring this one over. -4x plus 2y equals +6. So 4x minus 4x is 0. -2y plus 2y is 0. So on this side, I'm left with 0 right now. -6 plus 6, wow, is 0. If you get a true statement, so for example, this says 0 equals 0. If it is true, I could have 5 equals 5, 3 equals 3. As long as it's a true statement, then we would call this infinitely many solutions, which means every single point on either one of those lines is a solution. And the reason for that is because they're exactly the same line. If we solve this for y on both of them, we would discover that they both have the exact same. So let's look at this. Example 2. We have -2x plus y equals 3. So if I'm solving for y, I'm going to add 2x to both sides. I have y equals 2x plus 3. I just put it in slope-intercept form right there. My second equation was -4x plus 2y equals 6. So I'm going to add 4x. Bring down this 2y. I have 4x plus 6. Divide each term by 2. And I get y equals 4 divided by 2 is 2x. 6 divided by 2 is 3. Notice y equals 2x plus 3. Y equals 2x plus 3. They're exactly the same line, which means they are stacked directly on top of each other. So every single point on the blue marker is touching every single point on the pink marker. So every single thing. And remember, lines go on and on forever and ever and ever, which is why this one is the one we call infinitely many solutions. So every dot on both of those lines touch one another. All right, so let's take a look at example 3. You buy 1 bag of dog food and 2 bags of treats online for a total of $48. A few weeks later, you buy 2 bags of the same dog food and 4 bags of the same treats for a total of $96. Find the price of each bag of food and each bag of treats. So first, I have to start out by writing an equation. So I'm going to call the bag of dog food my x. So we'll highlight that one. And then I'm going to call the treats the y. Okay, so we have 1x, or just x, plus 2y, we have 2 bags of treats, equals $48. Then I have 2x plus 4y equals $96. So just like always, we are trying to figure out the cost. We got to solve for one of the variables first. So I'm going to rewrite these down here in my notebook. Example 3, x plus 2y equals 48, and 2x plus 4y equals 96. So I actually choose this top equation here, and multiply that all by 2. So I have 2x plus 4y equals 96, and then I have 2x plus 4y equals 96, and I'm going to subtract. 2x minus 2x is 0, 4y minus 4y is 0, 96 minus 96 is 0. So I've discovered that 0 equals 0. So I know that this means I have infinitely many solutions. But what does that mean about my bags of dog food and my bags of treats? Well, for starters, if we're buying a quantity of treats and dog food, we can't have a negative price, right? So we know that it has to be a positive number. The problem is I don't have enough information right now because every single point on that line, all the positive points, are going to give me a true solution for this. So right, this one, I would have to say that I need more information. So if I was trying to solve this, I would need more information. So currently, we can't solve it with the information that we have. And you're going to have instances like that where you're going to have to decide, okay, do I have what I need in order to get the price or the amount, whatever it is. I'm just going to put cost for that. So we need more information because right now we've eliminated both things and we don't know what the cost of each one would be. This is lesson 5.6. In lesson 5.6, we're going to talk about linear inequalities. The solution to a linear inequality is an ordered pair in the form xy that makes the inequality true. So we have dealt with inequalities before, but they were not linear inequalities. So linear inequalities take the format similar to linear equations. In example 1, we're going to tell whether the point we're given is a solution. So for letter A, we have the equation 2x plus y is less than negative 3. So it's linear because we're dealing with our two variables, and we could put it in the format that's similar to y equals mx plus b, with the exception of the equal sign now being an inequality. That means that there's more than one number that could be true for this line. So if I'm trying to test, I want to test to see if the point negative 1, 9 is a solution. So I'm going to plug in negative 1 for x, and I'm going to plug in 9 for y. So I have 2 times negative 1 plus 9 is less than negative 3. So we're going to simplify both sides. 2 times negative 1 is negative 2 plus 9 is less than negative 3. Negative 2 plus 9 is 7. Is 7 less than negative 3? As a matter of fact, this is not. 7 is not less than negative 3. So the point negative 1, 9 is not a solution. Does not make it true. For equation B, we have x minus 3y is greater than or equal to 8. And the point we're going to test is 2, negative 2. So I'm going to plug in 2 for x, and I'm going to plug in negative 2 for y. So I have 2 minus 3 times negative 2 is greater than or equal to 8. So I want to take care of my multiplication first. Negative 3 times negative 2 is positive 6. Bring down this 2. Greater than or equal to 8. 2 plus 2 is 8. Is 8 greater than or equal to 8? Yes, it is. So this is a solution. Now, if I had an inequality that said 8 is greater than 8, I would have said no, it's not a solution because 8 is not greater than 8. But because this has or equal to, I can have the same number on both sides of the inequality. I also could have any number that is larger than 8. So I could have 9, 10, 1 million. Any of those numbers that are greater than 8 would also have given me yes as a solution. All right, so let's take a look. When we're graphing linear inequalities, we have our less than or equal to symbols, we have our greater than and our less than symbols. When we're graphing, remember when we did our number line graphs and we had open circles and closed circles. So we have a very similar circumstance here with our linear graphs. So for an or equal to, it's going to be a solid line. Okay, so anything on that line would be included, much like the closed circle when we were doing our number line graphs. And when we have just less than or just greater than, we will have a dashed line because if it falls on the line, it's not a solution. So for example, this 8 would fall on the line, it's a solution because it's or equal to. This negative 1, 9, if it was on the line, would not be a solution because it's a dashed line. Okay, so let's take a look at some of these graphs. So if I'm looking at this, it's an or equal to, so I know that it's going to be a solid line. I'm going to start just like I did with our linear equations. So if I'm graphing it, I want to think about it kind of like when I had y equals 2. So I know y equals 2 means that I have a slope of 0 and I have a y-intercept of positive 2. So it's going to look like this. I'm going to have points on either side, but this is a solid line that goes through the point y equals 2. So solid because of the or equal to, and any value that shows up on this line would be a solution. Now, the second part to this is we do what's called shading because not just the numbers on the line are solutions. So what I want to do is I want to test a point and see if it will work. So if I'm testing, and honestly, I always like to test whenever possible, I like to test 0, 0 because it's an easy one to work with. So I'm going to test 0, 0. So I plug in 0 for y. So y is 0. Y is less than or equal to 2. Is 0 less than or equal to 2? Yes, because 0 is less than or equal to 2. 0, 0 is a solution. So I will shade everything below this line because that's where 0, 0 shows up. If I tested it and it was no, I would shade the opposite side of the line. So looking at my graph here, this one we could do our x and y intercepts because it's not in slope intercept form. So if I'm looking at it, it's similar to when we had our linear equation. So negative x plus 2y equals 2. So if I'm looking for my x intercept, so what is the x value when y is 0? So I have negative 1x equals 2. So divide by negative 1, I get x equals negative 2. So my x-intercept here, by the way, I know that it's going to be a dashed line. So I have x equals negative 2. And then I'm going to do the same thing. What's my y value when x is 0? So 2y equals 2, divide by 2, y equals 1. So my y-intercept is positive 1. And remember, I only need 2 points to make a line. So I will connect these using a dashed line. And I want to fill up the entire graph with my line because lines go on forever. And I want to make sure that my shading doesn't end up in a section that it shouldn't be, especially if I'm trying to test a point later with my graph. So I'm going to test 0, 0 because it's not on the line. If it was on the line, I'd have to choose a different point. So I'm testing 0, 0. So I have 0 for x. So negative 1 times 0 plus 2 times 0 equals 2. All right, so 0 plus 0 is 0. Oops, I have to use my inequality symbol in this disorder. Not the equals. There we go. So is 0 greater than 2? No, it's not greater than 2. Because it's not greater than 2, then I am going to shade everything that is not on the side where 0, 0 is. So everything up here. So all the numbers and points above that line would be solutions. And I could test them again to make sure if I needed to. All right, so example 4 says you can spend at most $12 on red peppers and tomatoes for salsa. Red peppers cost $4 per pound and tomatoes cost $3 per pound. Write and graph an inequality that represents the amounts of red peppers and tomatoes you can buy. Identify and interpret 2 solutions of the inequality. So let's think about some important information here. We know that we have at most $12. So I have to spend $12 or less. So that's the most, $12 or less. And I know that red peppers cost $4 per pound. So I'm going to use X for my red peppers. And tomatoes cost $3 per pound. So I'll use Y for those. So X equals peppers. Y equals tomatoes. Okay. So if I'm going to graph, I can either choose to graph it in standard form, or, especially if they're asking us for a slope-intercept form of this equation, I need to get Y by itself. So I'm going to subtract 4X from both sides. I'm going to bring down this 3Y. Less than or equal to negative 4x plus 12. I just did that, so it's matching more with our slope-intercept format. Divide each term by 3. And I have y is less than or equal to negative 4/3 x plus 4. So there is my equation. I'm going to write that onto this paper so we don't forget. Y equals negative 4/3 x plus 4. So I start with my y-intercept. Whoops, I wrote an equal sign. There we go. Less than or equal to. So I'm starting with 4 as my y-intercept. I know it's a solid line this time, so I have 4. There we go. And I'm going down 4 and over 3. 1, 2, 3, 4. 1, 2, 3. All right, so connect these. Alrighty, and if I am looking at this information, first of all, I can't go below because I can't deal with, I'm not going to be dealing with negative quantities of money. And I can't go up past here because I'm not going to be dealing with negative quantities of vegetables. Okay, so if I'm looking at this and I test 0, 0, for example, so 0 is less than or equal to negative 4/3 times 0 plus 4. So 0 less than or equal to 0 plus 4. Is 0 less than 4? Yes, 0 is less than 4. So all of the points in this lower section down here would be solutions. Now I'm going to try and lightly shade this. Actually, I think I'll use a pencil for shading just so that we can see the point values a little bit easier. That's everything down in this area here. So when it says identify and interpret 2 solutions for the inequality, well, I could choose any of these points down here in this corner. I also, because it's a solid line, I could choose any of the points that are on the line as well. So let's say I chose 0, 4. What that means is I could buy my x value is 0. Remember that x was our peppers. So I could buy 0 peppers and 4 tomatoes, and I would stay within my limits of $12 for my vegetables. I could choose this point down here, 3, 0. 3, 0, I could buy 3 peppers, 0 tomatoes. I would stay within my limits of my $12. However, they're making salsa, right? So does it make sense to buy all peppers and no tomatoes, or all tomatoes and no peppers? It doesn't really. So I honestly want to pick another one, and I'm going to choose this point right here. So if I choose this point right here, that is the point 1, 2. And that means I can buy 1 pepper and 2 tomatoes, and I would stay within the limits of my $12 in order to make my salsa. So I could pick any of the numbers on the line or below this line for this situation, and I would have values that would work. But remember, because this is tomatoes and peppers, I need to stick with the whole numbers because the store is going to only buy half a tomato or half of a pepper. If we're talking about things that are not whole quantities that we would need to buy as a whole thing, then I'd be able to use decimals or fractions in other situations. This one, since we're talking about tomatoes and peppers, I have to work with those whole numbers in order to get the proper lineup. This is lesson 5.7a. In lesson 5.7a, we're going to continue talking about linear inequalities, but this time we're going to talk about systems of linear inequalities, just like systems of equations. When you have a solution, it's an ordered pair that's true for both inequalities. So if we look at example 1, problem A, we are testing the inequality y is less than 5 with the point -1, 5. So my y value is 5. So I'm going to plug in 5 for y. So is 5 less than 5? In this instance, no, it is not less than 5. Oops, I want to use a different color. So it's not less than 5. So right now it's looking like this is not a solution. Sometimes we check that one first to check the other one. So let's see if it would have worked for the original, the second inequality. So y is greater than x minus 4. So in this case, I would plug in 5 for y still, because we're testing the same point. So 5 for y is greater than -1 minus 4. Well, -1 minus 4 is -5. Is 5 greater than -5? Yes, it is. But because this does not work, then for the first one, we would have to say that this point, -1, 5, is not a solution. For letter B, we have the inequality y is greater than or equal to 3x plus 1, and we're testing the point 1, 4. So for my x value, we've got 1. So we'll plug that in here for x. So I have 3 times 1 plus 1, and we know that our y value is 4. So we're going to plug in 4 for y. All right, so we have 4 greater than or equal to 3 times 1 is 4. Oh my gosh, 3 times 1 is 3. Get ahead of yourself here, Mr. Weber. Plus 1. So is 4 greater than or equal to 3 plus 1 is 4. Is 4 greater than or equal to 4? Yes. So far, so good. But remember, we have to check both inequalities. So my second one is y is greater than x minus 1. So I've got 4 for y is greater than 1 minus 1. 1 minus 1 is 0. Is 4 greater than 0? Yes. Therefore, because these two things here are true, then I would say yes, that point is a solution to this system. All right, so let's look at the graph of a system. So if I look at this next part, it tells me that the graph of a graph of a system of linear inequalities is the graph of all the solutions to the system. So once I graph these two inequalities, then I will be able to see the region that is a solution for all. So when we did just one line, remember we shaded either above the line or below the line, and the shading told us the solution to that inequality. Well, now we have to do this for both inequalities in our system. So let's take a look at that first inequality in part A, and let's figure out our x and y intercepts in order to graph this. So if I plug in 0 for x, that leaves me with -2y is greater than 4. If I divide by -2, then I have y, and I have -2 here. Remember, when I divide by negative, I got to flip the sign. So for this line, y is less than -2. So I'm looking at my y-intercept is -2. Then for my x-intercept, I have 2x is greater than 4. Divide by 2. And I have x and 2. But remember, we're finding our intercepts, so I don't even need the inequality symbol when I find this, because I'm just trying to figure out what the value is equal to, where the line is touching those axes. So x-intercept is also 2. So right here. Now I'll go back and look at my original symbol. So this was a greater than, no equal to, so we're going to have a dashed line. Let's test point 0, 0, like we've done in the past. All right, so 2 times 0 is 0. 2 times 0 is 0. 0 minus 0 is 0. Is 0 greater than 4? No, it's not. Therefore, we have to shade away from that point 0, 0. So let's get our dashed line on here. And again, use up as much of the graph space as you can so that you can see the full range of your solutions. And then it's everything underneath the line over here, away from 0, 0. All right, let's test our second inequality. We had x minus y is less than or equal to -3. So again, we're going to find our intercepts. We have points to graph. So if I plug in 0 for x, I have -y equals -3. Divide by -1, we get y equals +3. So on my y-axis, I'm going to be up here at +3. All right, same thing, but now we're going to plug in 0 for y. So I have x equals -3. All right, so my x-axis is -3. Now this is or equal to, so I'm going to have a solid line here. Goodness sakes. And we're going to test 0, 0. 0 minus 0 is less than or equal to -3. Not true, so I have to shade away. So this one would be no solution because there's no place where these two lines overlap. All the space in between them is blank, so there's no space for those to overlap. And just like when we had our systems of equations, if you notice, these two equations or inequalities, if we put them in slope-intercept form, would have the same slope, which is another way that we can realize that they would never touch. My lines are just a little bit off, so they look like they're starting to go together, but they have the same slope, so they would never touch. They're parallel lines, so nothing in between is shaded for these ones because of the way that the inequality symbols matched with them having the same slope. So nothing in between them this time was shaded, so it's a no solution. Now, if I have parallel lines and let's say this one I shaded up and this one I shaded down, then we would have the space between the two lines that would fit as our solutions. But this one happens to be opposite sides of it, so it's a no solution. For letter B, if we're going to graph this, then the nice thing is these are already in a slope-intercept format for us. So we're going to put a dot at -3, and then we're going to use our slope. We're going to move up 2 and right 1. 1, 2, and right 1. Help me to get a little bit straighter of a line. And this is just greater than, so we're going to have a dotted line for that. There we go. And if we test our point 0, 0, so I put in 0 for x and 0 for y. 2 times 0 is 0. 0 minus 3 is -3. Is 0 greater than -3? Yes. So we're going to shade everything above. And I'm going to try to go lightly in case I need to use those other numbers in the future. For my second line, I have a y-intercept of +1 and a slope of 1/2. So I'm going to go up 1 and right 2. I'm also going to go down 1 and left 2. And then this is an or equal to, so I know that I have a solid line for that one. There we go. I'm going to test my point 0, 0 right here. So 0 times 1/2 is 0. 0 plus 1 is 1. So is 0 greater than or equal to 1? For this one, it is not. So I have to shade all of the space away from 0, 0, which is going to be everything up here. So for us to have solutions to this system of inequalities, it's all of the area where the blue and the pink overlap. So look at here. This space here would be a solution for pink, but not blue. This would be a solution for blue, but not pink. So our pink, actually, these dotted space here, so it can't be on this blue line, and then this entire pink line and everything in this space here. So I'm going to make it purple because blue and pink can make purple. So if it's on our pink line over here, solution. If it's on our blue line here, not a solution because the blue line is dotted and the pink line is solid, and it's everything from these two spaces that way. So if I wanted to pick a number off of here as a solution, just one of the solutions, I could say right there, and it would be 0, 3. That's a solution. Or right here, which is 6, 3. That's a solution. Oops, negative 6, 3. So lots of solutions for that. This is lesson 5.7b. In lesson 5.7b, we're going to continue to talk about systems of linear inequalities. And we are also going to focus on writing those systems from graphs. So if we look at graph A, we have this dotted line here, or dashed. That means that we know it's a less than or it's a greater than, but it is not an or equal to, right? Because it cannot be on the line and be considered a solution. So if we're looking at it, remember, we always want to start by finding that y-intercept. So the spot where that pink line touches the y-axis, it touches right up here at positive 2. So I know that I'm going to have plus 2 in my inequality. I know that if it's a linear inequality, I know it's going to look in the form of y equals mx plus b when we had equations. So it's going to look similar to that. I need to find the slope. So I have a point here and I have a point down here. So my slope is down 1, 2 over 1, 2. So my slope is 1x or just x. Then I have to test. Now, if you're looking down here at the bottom, this pink, because there's shading here, this pink is actually part of that whole section are the solutions. So if we tested our point 0, 0, which is right in here, it's part of the solution set. So if it is part of the solution, it has to be a true inequality. So 0 has to be, and we have 0 plus 2, so that's 2. So 0 is less than 2 for this one. So y is less than x plus 2. That's the line or the inequality for this diagonal line here. For the vertical line, again, also a dashed line. So we know it's going to be just a greater or just a less than, no or equal to. We know it's going to have the y equals mx plus b format. So there's a y, there's an x. If I'm looking at it, though, it's a vertical line. And since it is a vertical line, remember that we actually don't have y equals. Because it is a vertical line, we have usually, if it's an equation, we have x equals. Well, in this instance, because it's an inequality, we have to look and see, is it greater, is it less? But we do know that it's going through the x-axis at 3. So as I look at this, again, here's the shading that we had as part of our solution set, because they gave us that shading as part of our answer. So we have all of this, including, again, our point 0, 0. So if I plug in 0 for x, is 0 greater than 3 or less than 3? 0 is less than 3. So my second inequality as part of my system is x is less than 3. Now, if we look, let's just kind of darken this up. So we have our dashed line here, but everything to the left of those dashed lines are part of the solution set. So here's our system. Y is less than x plus 2, x is less than 3. Together, they make this purple solution set. Looking at B, if we're noticing, we have our y-axis is here, but notice we do have a vertical line. So this vertical line, again, going to start x equals if we had an equation, but in this instance, it's an inequality. So we've got x. It's going through the point 3. My solution set, if you notice, is this shaded here. So I know that this part of the line was shaded. If I tested 0, 0, so right here, it was part of the solution. So if it's part of the solution, we have to make a true inequality. So is 0 greater than 3 or less than 3? 0 is less than 3. So our inequality is x is less than or equal to 3 because it's that solid line. My second line in this one, dashed line. So we know it's just a greater or just a less. I know that the y-intercept is down here at -1. So I have to have -1 as part of my inequality. It's not vertical, so I know I'm going to have the y equals mx plus b format. So I need to look for my slope. I have a point here at 3, 1, and I have a point down here at 0, -1. So to get from here to here, I'm going to go up 1, 2, and over 1, 2, 3. So it looks like our slope is 2/3. So up 2 and right 3, 2/3. Now let's look, since again, the solutions are up here, based on the shading that they gave us. 0, 0 again is included. So I have to say, okay, it's got to be true. So 0 for y, 0 for x. This is 0 and -1. So is 0 greater than -1 or less than -1? 0 is greater than -1. Since it's dashed, remember, it's just greater. So we have x is less than or equal to 3. Y is greater than 2/3 x minus 1. This is our system for that set of inequalities. Example 2, we're going to look at a real-world problem related to our systems of inequalities. A company is loading recliners and sofas onto a trailer that has a volume of about 3,800 cubic feet. Each recliner takes up about 40 cubic feet, and each sofa takes up about 80 cubic feet. The company wants the shipment to have at least 30 recliners and more than 25 sofas. Writing graph a system that represents the situation. Give an example of the numbers of recliners and sofas the company can have in the shipment. So if we're looking at it in general, starting out, we know that there is 3,800 cubic feet available space in this trailer. That's important for my inequality. I know that recliners take 40 cubic feet for each one, but I don't know how many I'm going to need. So I'm going to use 40 and I'm going to use X for recliners. You could use R if you wanted. I find it easier just to keep with X and Y's and just label which is which. I also have to take into account the sofas, which are 80 cubic feet apiece. So they combine. I'm going to use Y for the sofas. And it says, if we look, that the volume is 3,800 cubic feet. So we can have 3,800 cubic feet exactly, but we can't have more. So we have to have less than or equal to 3,800 cubic feet for that first inequality. For my second inequality, I'm looking down here and I see it says the company wants the shipment to have at least 30 recliners. So I'm gonna look at that individually, at least 30 recliners. My X were my recliners. I know we need at least 30. So 30 is the smallest amount that we want to have. We could have more than that. We could have 30. So X has to be greater than or equal to 30. That means it includes 30 or anything larger. It also says we have to have more than 25 sofas. So Y are the sofas. We know 25 is our measurement. And it says more than. I can't have 25. It has to exceed 25 for it to be true. So I have to have greater than 25 sofas for my for that requirement. So I'm going to graph 3 lines on this one set of axes. And I'm going to label each line on my axis by 5s. So X and Y, I'm going to count each one of these by 5. 35, 40, 45, 50, 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. And again, this is our x-axis, so this is talking about recliners. And it's a number of recliners, right? And the sofas are the y-axis, so we've got number of sofas on the y-axis. So let's start with the 2 smaller inequalities. We know that x is greater than or equal to 30 is going to be a vertical line because it's like the x equals that we're used to from the past. So I know that it has to touch the x-axis down here at 30. And it's going to be a vertical line, so going straight up and down. Also, I know that it is or equal to. That way we know that this is the one I did in pink. So it's or equal to, so I know it's going to be a solid line right here on 30. Then I have my sofas. Sofas are greater than 25. Just like when we had our equations, if it starts y and just has a number, we know it's a horizontal line because that slope is 0. And it's going to go through 25 for this one. Also, it's dashed because it doesn't say or equal to. It just says greater than. All right. So these are my lines. I need to go back and shade them. So let's test our point down here, 0, 0. And for 0, 0, is 0 greater than or equal to 30? No, it's not greater than or equal to 30, so I have to shade the opposite side of the line. So everything on this side, I just kind of skipped over that blue so it doesn't smear. Testing it again. So 0 is greater than 25, also false. So this time I have to shade above. So if we're just looking at these 2 inequalities, this square right here, or this rectangle, would be our solution set. Problem is, we have a third equation that we have to keep in mind. So we're looking at 40x plus 80y is less than or equal to 3,800. So as we're doing this, we should plug in 0 for x, find our y-intercept. Plug in 0 for y, find our x-intercept. We also could try putting our equation into slope-intercept form. And looking at these, if I were to plug in 0 for x, I would get a y-intercept of 47.5. And if I plug in 0 for y, I'm going to get an x-intercept of 95. My x-axis doesn't go up to 95. So I would choose to not do this method just because of the graph that we have. So let's put it into slope-intercept form. So we have 40x plus 80y less than or equal to 3,800. So we're going to subtract 40x. We've got 80y is less than or equal to negative 40x plus 3,800. Divide each term by 80. That leaves us with y is less than or equal to negative 1/2 x plus 47.5. So our y-intercept is 47.5. And if you notice, since we counted by 5s, halfway between 45 and 50 is 47.5. And then we're going down 1 and over 2. Or since we counted by 5s, we're going down 5 and over 10. Okay, so we're going down, that's 250, 5 and over 10. So 5, 10, put a dot. So down 5 over 10. Down 5 over 10. And it is or equal to, so we know it's going to be a solid line. There we go. If we were to plug in 0, let's use this one here. 0 is less than or equal to, since that makes 0, 47.5. Is 0 less than or equal to 47.5? Yes. So for this one, we're actually shading down towards that 0, 0. Again, just trying to not interact with these lines. So what we notice here, in order to be part of our solution, the only spot where all 3 colors overlap, we've got our solid line here. We have, ooh, I went too far. We have our dashed line here, and we have our solid line. So that small little triangle right there is our solution set. So if I'm looking at this carefully, one of the points that I could choose is 35, 35 and almost to 30, so it's about 28. So if we have the point 35, 28 for this, that means that we could have 35 recliners, 28 sofas, and we would still be within the requirements of having more than or equal to 30 recliners, more than 25 sofas, and we kept our cubic feet less than or equal to 3,800.